This is before. This is after. Later you'll see planar projections from the top, front, and side. One of those will look like this. Professionals in the field of anatomy can recognize specific landmarks on various anatomical structures. The dots in these clusters are from 14 landmarks on the windpipe from each of 10 patients. For the planar projections, I split the top and bottom into views from top and bottom. That's to avoid overlap where landmarks belonging to one cluster could show up in the image of another. Clusters on the left came directly from a Procrustes representation. On the right, you see the result after removing the affine deformations in 3 dimensions, 3D. It's clear that these clusters converge, resulting in substantially less dispersion. Theoretically, in fact, if affine shear and unequal scaling were the only deformations present, those 14 clusters would shrink almost all the way down to just 14 points. Okay, that's enough of my putting the cart before the horse. You'll see a more complete set of landmark plots later in this presentation. First, it's time for a brief discussion of background leading up to how this all came about, where all this work is now, where it can be accessed, and where it appears to be headed. 2 principal names, Bookstein and Zeldich, are authors of 2 key references cited now. Bookstein 1997 showed an example with almost 19% reduction in variance from original Procrustes coordinates of brain landmark data that he put at the upper left of his figure 9 on page 108. It isn't essential to replicate that figure here, since you've already seen an example showing before and after images for the case of immediate interest, the windpipe. Bookstein goes on to say that it's worth uncovering that deformation before going after another type of deformation called the non-uniform part. That will be explained later by citing another reference here in a slide entitled Thin Plate Spline. But first, it's important to continue the present train of thought. Bookstein's 19% improvement is a variance reduction in his figure 9. Without reproducing that figure here, the viewer can understand that different patients will have a different spread of landmarks, and so, if those variations correlate with any type of affliction, we have strong motivation to pursue that diagnostic capability. Now, for a specific example, immediately following Bookstein's Procrustes fit, but before extracting deformations, variance is 0.0074. He shows that in the upper left part of his figure. Variance with affine deformations removed, shown in the upper right of his figure, is 0.0060. So, with variance reduced to this fraction of its original Procrustes value, we can think of a 1 sigma ratio characterized as the square root of that number, or about 90%. I need to acknowledge there's a little more to this. Bookstein's figure 9 covers 2 dimensions, not just 1. Right now I could go into the difference between variation of a point position along a straight line versus dispersion of bullets centered around a bullseye on a target, but we don't need that distraction from our main thrust. For now, it's enough to note comparative spread in each of the 2 directions among positions depicted in before and after views of landmark clusters. In Bookstein's example, the latter are spread 90% as much as the former. Or, going back to the topic of reduction in variance, that corresponds to an improvement of 1 minus 0.8108, or almost 19%. Okay, how did he get that? Bookstein achieved that using equations 624 and 638 from the 6-page mathematical derivation in Chapter 6 of Zeldich's book on pages 137 through 142. I'm citing those instead of equations 9 from his paper because that version was printed with a typo. Anyway, those equations don't have to be shown here either, because I had to make a major change in the approach from 2D to 3D. To do that, an immediate task can be expressed this way. Given a set of input coordinates, there's a sharp distinction between determination of output coordinates from a given transformation, determination of a transformation to produce specified output coordinates. These two things. The first objective is always easy. It is now essential to recognize what's available for the second case. Existing sources provide means to compute a transformation from before and after coordinates for the two cases. Here, the first one is the easy one. The second case is what Bookstein provided. But now, to obtain the results shown here, I had to include both 3D applicability and affine deformations. To talk about that, I'll begin with a very short review of an analytical process called the Procrustes representation for morphometrics. This will begin by looking at an attribute that's dominant for us, size, which has different types of conditions attached to it here. Uniform scale change, expansion or contraction by the same percentage in each direction, is self-explanatory. But the other two cases need a little more definition. For the case exemplified by changing a square to a rectangle, a larger width comes with a shorter length. In a similar way, a change from rectangle to parallelogram happens with the standardization of overall size to be described shortly. These latter two affect shape, so we'll call those shape states. The square to rectangle one will be called unequal scaling, and the rectangle to parallelogram one is shear. Now we'll include those in a list of effects that we care about. Bookstein's 1997 manuscript is again useful here for his description of the Procrustes representation in 2D. For the first three items on this list, it makes use of an affine transformation, providing a linear relation between input and output vectors. Both components of the 2D vectors can differ in all of the following ways. The vectors may have different locations, orientation, size, and might not be seen from the same perspective. That last attribute, perspective, is irrelevant for our purposes, so we can leave that out of all further discussion here. So we subdivide our list of effects this way. Translation causes a shift in location for 2D that can happen in two directions. And the rest of the effects I'll identify now have only one degree of freedom. Rotation changes the orientation. Uniform scaling changes the size without affecting the shape. And the affine list is completed by adding the unequal scaling and shear. So here's the 2D process. It begins with a Procrustes fit. From the landmark set of each patient, average his or her horizontal and vertical coordinates to get the centroid. Put the centroid at the origin by subtracting its coordinates from every landmark location. Doing that for both x and y takes care of the translation. Bookstein then shows how one rotation for each separate patient minimizes a measure of total separation over all landmarks. Then scrunch the size of each patient down by whatever amount will represent everyone as having uniform size. Then you have a Procrustes fit, and the only thing left on our list is shape. Bookstein produced an improvement beyond Procrustes by finding a combination of unequal scaling and shear that further reduces the total separation among a transformed set of landmarks. Applying it to his brain landmark data, he achieved that 19% variance reduction by his documented 6-page derivation I cited earlier. For those interested in the math, both that reduction and the earlier minimization for Procrustes used least squares criteria. Okay, now we're finally ready to talk about the procedure for 3D. The first step is a simple extension of what was done before. The centroid is computed, but now in 3D. There are now 3 degrees of freedom to put each patient's centroid at the same reference point, the origin. Now there are also 3 more for rotation. To accomplish that, we have to go a little further than what was required for 2D. We have to align 3 principal directions. In correspondence to the way Bookstein used one rotation for minimizing total departures among landmark sets for different patients, we need something more for 3D. To describe that here, I'll do a very short summary, only for those interested in the math that was used. If mentioning principal directions conjures up ideas about eigenvectors of an inertia matrix, that's close, but there's a little more to it. We use singular value decomposition. Again, that's just for those who want to know. If not, that's no problem. The program takes care of it. Now, with all the centroids in place and the directions all aligned, you have numbers for each patient's coordinates. In our data set with 14 landmarks in 3D, that's a 3 by 14 array of numbers, some positive and some negative, with 0 average in each direction. Now, divide all those 42 numbers by the square root of the sum of squares of all 42. That gives you 42 new numbers. They're dimensionless because you've divided length by length. So it doesn't matter whether your landmarks are measured in centimeters, millimeters, or any other units. The sum of squares of all 42 dimensionless numbers is 1. Now you have the Procrustes fit. Beyond the Procrustes fit procedure just described, of course, I had to come up with a transformation that would do in 3D what Bookstein did for 2D by his 6-page math derivation in Zeldich's book. For example, rather than replacing a square by a rectangle in 2 dimensions, we now replace a cube by a brick-shaped object in 3 dimensions, again with overall size constrained by normalization. Now there are 2 of those shape states from unequal scaling, and 3 shear states, giving a total of 5 shape states in 3D. Clearly there's no way to cover that here, so we finally reached the point to finish talking about the windpipe results. You've already seen the 3D images, so all we need now are the before and after views for planar projections of those 3D images as seen from the top, front, and side. Projecting can cause some clusters to appear overlapped, for example from front and back, or top and bottom, or left and right. So I divided the 14 landmark clusters to get around that. It can't be prevented completely, but at least it can be minimized. The split is roughly 50-50. It doesn't have to be even, as long as the number of clusters matches the number of landmarks, and the number of dots in each cluster matches the number of patients. Here they are. The XY plane looks like this. Viewed from this direction, you would think there are only 12 clusters. Landmarks from 2 of them are eclipsed by others. Splitting the 14 into 2 groups helps, but doesn't completely eliminate that. This is the XZ plane, and the YZ plane looks like this. There are many more plots, but with the time remaining, only a few high priority items will be discussed. First, the main point of this presentation is intended to demonstrate a very substantial shrinkage in the spread of these clusters. The variance comes down by more than a factor of 9. To put this in perspective, that's almost a 90% reduction. Compare that against the 19% reduction described for the 2D example mentioned earlier. What I've concluded from these results can be stated this way. Shape states in 3D offer much more than 2D, enough to become a useful diagnostic tool. It wouldn't be too surprising to discover future correlations between certain afflictions and shape irregularities. All the results you've seen so far were for 10 male patients. Now I'll show the results for 20 patients, 10 male and 10 female. Once again, we notice some eclipsing. It looks as if the females outnumber the males. That's because the female landmarks were plotted last. This is before and after, and now the planar projections. XY looks like this. Here's the XZ plane and the YZ plane. Finally, you'll see an example showing departures from the deformation model. At the top, those deviations are shown for all male patients at each landmark. At the bottom, the same information is regrouped to show all landmark deviations of each male patient. Departures at landmark number 12 are unusually large for patient number 7 and especially number 9. All this, and I've hardly even mentioned the non-uniform deformations. They're called non-uniform because they apply only locally. They're not applicable to the entire structure. Those are handled by another processing algorithm, the thin plate spline, in accordance with the reference cited here. As I pledged earlier, here's the information you'll need to get the program. It offers a ton of graphics work, including both uniform affine and non-uniform TPS deformations, plus another bunch of graphical properties that I'm not the one qualified to describe. The benefit it offers to you is very easy to describe. You can use the program to process your own landmark data from any other anatomical site. It is our genuine hope that this work, a collaboration from 3 individuals in 3 very different areas, will make life easier for many through improved diagnostics in 3 dimensions throughout.